Hello, good day everyone. Welcome to our astronomy class. We will discuss about the ancient astronomy. Newton's great synthesis. It was the genius of Isaac Newton that found a conceptual framework that completely explained the observations and rules assembled by Galileo, Brahe, Kepler, and others. Newton was born in Lincolnshire, England, in the year after Galileo's death. Against the advice of his mother, who wanted him to stay home and help with the family farm, he entered Trinity College at Cambridge in 1661 and 8 years later was appointed professor of mathematics. Among Newton's contemporaries in England were architect Christopher Wren, authors Arthur Ben and Daniel Defoe, and composer G. F. Handel. There were three laws made by Newton. Newton's first law, which states that every object will continue to be in a state of rest or move at a constant speed in a straight line unless it is compelled to change by an outside force. Newton's second law says the change of motion of a body is proportional to and in the direction of the force acting on it. And Newton's third law, for every action there is an equal and opposite reaction, or the mutual actions of two bodies upon each other are always equal and act in opposite directions. Newton's first law is a restatement of one of Galileo's discoveries, called the conservation of momentum. The law states that in the absence of any outside influence, there is a measure of a body's motion, called its momentum, that remains unchanged. You may have heard the term momentum used in everyday expressions, such as, "This bill in Congress has a lot of momentum. It's going to be hard to stop." Newton's first law is sometimes called the law of inertia, where inertia is the tendency of objects to keep doing what they are already doing. In other words, a stationary object stays put and a moving object keeps moving unless some force intervenes. Now, what is momentum? Let's define the precise meaning of momentum. It depends on three factors. 1. Speed. How fast a body moves. 0 if it is stationary. 2. The direction of its motion. And 3. Its mass, a measure of the amount of matter in a body, which we will discuss later. Scientists use the term velocity to describe the speed and direction of motion. For example, 20 kilometers per hour due south is velocity, whereas 20 kilometers per hour just by itself is speed. Momentum then can be defined as an object's mass times its velocity. It's not so easy to see this rule in action in the everyday world because of the many forces acting on a body at any one time. One important force is friction, which generally slows things down. If you roll a ball along the sidewalk, it would eventually come down to a stop because the sidewalk exerts a rubbing force on the ball. But in the space between the stars, where there is so little matter that friction is insignificant, objects can in fact continue to move indefinitely. The momentum of a body can change only under the action of an outside influence. Newton's second law expresses force in terms of its ability to change momentum with time. A force, a push or a pull, has both size and direction. When a force is applied to a body, the momentum changes in the direction of the applied force. This means that a force is required to change either the speed or the direction of a body, or both. That is, to start it moving, to speed it up, to slow it down, to stop it, or to change its direction. The rate of change in an object's velocity is called acceleration. Newton showed that the acceleration of a body was proportional to the force being applied to it. Suppose that after a long period of reading, you push an astronomy book away from you on a long, smooth table. We use a smooth table so we can ignore friction. If you push the book steadily, it will continue to speed up as long as you are pushing it. The harder you push the book, the larger its acceleration will be. How much a force will accelerate an object is also determined by the object's mass. If you kept pushing a pen with the same force with which you pushed the textbook, the pen, having less mass, would be accelerated to a greater speed. Newton's third law is perhaps the most profound of the rules he discovered. Basically, it is a generalization of the first law, but it also gives us a way to define mass. If we consider a system of two or more objects isolated from outside influences, Newton's first law says that the total momentum of the objects should remain constant. Therefore, any change of momentum within the system must be balanced by another change that is equal and opposite so that the momentum of the entire system is not changed. This means that forces in nature do not occur alone. We find that in each situation there is always a pair of forces that are equal to and opposite each other. If a force is exerted on an object, it must be exerted by something else, and the object will exert an equal and opposite force back on that something. We can look at a simple example to demonstrate this. Suppose that an astronomy student and a skateboarder wants to jump from his second-story dorm window onto his board below, but we don't recommend you to try this. The force pulling him down after jumping is the force of gravity between him and Earth. Both he and Earth must experience the same total change of momentum because of the influence of these mutual forces. So, both the student and Earth are accelerated by each other's pull. But take note, in our example, we use an image of the bird. So, however, the student does much more of the moving because Earth has enormously greater mass. It can experience the same change of momentum by accelerating only a very small amount. Things fall toward Earth all the time, but the acceleration of our planet as a result is far too small to be measured. A more obvious example of the mutual nature of forces between objects is familiar to all who have batted a baseball. The recoil you feel as you swing your bat shows that the ball exerts a force on it during the impact, just as the bat does on the ball. Similarly, when a rifle you are bracing on your shoulder is discharged, the force pushing the bullet out of the muzzle is equal to the force pushing backward upon the gun and your shoulder. This is the principle behind jet engines and rockets. The force that discharges the exhaust gases from the rear of the rocket is accompanied by the force that pushes the rocket forward. The exhaust gases need not push against air or earth. A rocket actually operates best in a vacuum. Let's take a look on mass, volume, and density. The volume of an object is the measure of the physical space it occupies. Volume is measured in cubic units such as cubic centimeters or liters. The volume is the size of an object. A penny and an inflated balloon may both have the same mass, but they have very different volumes. The reason is that they also have very different densities, which is a measure of how mass there is per unit volume. Specifically, density is the mass divided by the volume. Note that in everyday language we often use heavy and light as indication of density, rather than weight. As for instance, when we say that iron is heavy or that whipped cream is light. To sum up, mass is how much, volume is how big, and density is how tightly packed. A concept that is a bit more complex but important for understanding many astronomical objects is angular momentum, which is a measure of the rotation of a body as it revolves around some fixed point. As an example is a planet orbiting the Sun. The angular momentum of an object is defined as a product of its mass, its velocity, and its distance from the fixed point around which it revolves. If these three quantities remain constant, that is, if the motion of a particular object takes place at a constant velocity at a fixed distance from the spin center, then the angular momentum is also constant. Kepler's second law is a consequence of the conservation of angular momentum. As a planet approaches the Sun on its elliptical orbit and the distance to the spin center decreases, the planet speeds up to conserve the angular momentum. Similarly, when the planet is farther from the Sun, it moves more slowly. The conservation of angular momentum is illustrated by figure skaters who bring their arms and legs into spin more rapidly and extend their arms and legs to slow down. You can duplicate this yourself if on a well-oiled swivel stool by starting yourself spinning slowly with your arms extended and then pulling your arms in. Another example of the conservation of angular momentum is a shrinking cloud of dust or a star collapsing on itself. As material moves to a lesser distance from the spin center, the speed of the material increases to conserve angular momentum. Newton's universal law of gravitation. Newton's law of motion shows that objects at rest will stay at rest, and those in motion will continue moving uniformly in a straight line unless acted upon by a force. Thus, it is the straight line that defines the most natural state of motion. But the planets move in ellipses, not straight lines. Therefore, some force must be bending their paths. That force, Newton proposed, was gravity. Once Newton boldly hypothesized that there was a universal attraction among all bodies everywhere in space, he had to determine the exact nature of the attraction. The precise mathematical description of that gravitational force had to dictate that the planets move exactly as Kepler had described them to. Also, the gravitational force had to predict the correct behavior of falling bodies on Earth. As observed by Galileo, how must the force of gravity depend on distance in order for these conditions to be met? The answer to this question required mathematical tools that had not yet been developed, but this did not deter Isaac Newton, who invented what we today call calculus to deal with this problem. Eventually, he was able to conclude that the magnitude of the force of gravity must decrease with increasing distance between the Sun and a planet, or between any two objects, in proportion to the inverse square of their separation. In other words, if a planet were twice as far from the Sun, the force would be 1/2 squared, or 1/4 as large. Put the planet 3 times farther away and the force is 1/3 squared, or 1/9 as large. Newton also concluded that the gravitational attraction between two bodies must be proportional to their masses. The more mass an object has, the stronger the pull of its gravitational force. The gravitational attraction between any two objects is therefore given by one of the most famous equations in all of science, which is gravitational force is equals to G multiplied by m1, or mass 1, times mass 2 over r squared. So F here stands for the gravitational force between the two objects and the masses of the two objects, and r is their separation. G is a constant number known as the universal gravitational constant, and the equation itself symbolically summarizes Newton's universal law of gravitation. With such force and the laws of motion, Newton was able to show mathematically that the only orbits permitted were exactly those described by Kepler's laws. Newton's universal law of gravitation works for the planets, but is it really universal? The gravitational theory should also predict the observed acceleration of the Moon toward Earth as it orbits Earth, as well as of any object, say an apple dropped near Earth's surface. The falling of an apple is something we can measure easily, but can we use it to predict the motions of the Moon? Recall that according to Newton's second law, forces cause acceleration. Newton's universal law of gravitation says that the force acting upon an object toward Earth should be inversely proportional to the square of its distance from the center of Earth. Objects like apples at the surface of Earth at a distance of 1 Earth radius from the center of Earth are observed to accelerate downward at 9.8 meters per second. The Moon is 60 Earth radii away from the center of the Earth. If gravity gets weaker with distance squared, the acceleration the Moon experiences should be a lot less than for the apple. The acceleration should be 1 over 60 squared is equals to 1 over 3,600, or 3,600 times less, about 0.00272 meter per second squared. This is precisely the observed acceleration of the Moon in its orbit. As you shall see in the Moon does not fall to Earth with its acceleration, but falls around Earth. Imagine the thrill Newton must have felt to realize he had discovered and verified a law that holds for Earth, apples, the moon, and as far as he knew, everything in the universe. Gravity is a built-in property of mass. Whenever there are masses in the universe, they will interact by the force of gravitational attraction. The more mass there is, the greater the force of attraction. Here on Earth, the largest concentration of mass is, of course, the planet we stand on, and its pull dominates the gravitational interactions we experience. But everything with mass attracts everything else with mass anywhere in the universe. Newton's law also implies that gravity never becomes zero. It quickly gets weaker with distance, but it continues to act to some degree no matter how far away you get. The pull of the Sun is stronger at Mercury than at Pluto, but it can be felt far beyond Pluto, where astronomers have good evidence that it continuously makes enormous numbers of smaller icy bodies move around huge orbits, and the Sun's gravitational pull joins with the pull of billions of other stars to create the gravitational pull of our Milky Way galaxy. That force, in turn, can make other small galaxies orbit around the Milky Way, and so on. Why is it then, you may ask, that the astronauts aboard the space shuttle appears to have no gravitational forces acting on them when we see images on television of the astronauts and objects floating in the spacecraft? After all, the astronauts in the shuttle are only a few hundred kilometers above the surface of Earth, which is not a significant distance compared to the size of Earth, so gravity is certainly not a great deal weaker that much farther away. The astronauts feel weightless, meaning that they don't feel the gravitational force acting on them, for the same reason that passengers in an elevator whose cable has broken, or an airplane whose engines no longer work, feel weightless. They are falling. When falling, they are in free fall and accelerate at the same rate as everything around them, including their spacecraft or a camera with which they are taking photographs of Earth. When doing so, astronauts experience no additional forces and therefore feel weightless. Unlike the falling elevator passengers, however, the astronauts are falling around Earth, not to Earth. As a result, they will continue to fall and are said to be in orbit around Earth. The orbital motion and mass. Kepler's laws describe the orbits of the objects whose motions are described by Newton's laws of motion and the law of gravity. Knowing that gravity is a force that attracts planets towards the Sun, however, allowed Newton to rethink Kepler's third law. Recall that Kepler had found a relationship between the orbital period of a planet's revolution and its distance from the Sun. But Newton's formulation introduces the additional factor of the masses of the Sun, or m1, and the planet, m2, both expressed in units of the Sun's mass. Newton's universal law of gravitation can be used to show mathematically that this relationship is actually where A is the semi-major axis and B is the orbital period. Now let's take a look at calculating the effects of gravity. A planet, like Earth, is found orbiting its star at a distance of 1 astronomical unit in 0.71 Earth year. Can you see Newton's version of Kepler's third law to find the mass of the star? Now remember that compared to the mass of a star, the mass of an Earth-like planet can be considered negligible. In the formula, a cubed is equals to mass 1 plus mass 2 multiplied by p squared. The factor of mass 1 added to mass 2 would now be approximately equal to mass 1, the mass of the star, since the planet's mass is so small by comparison. Then the formula becomes a cubed is equals to mass 1 times p squared, and we can solve for mass 1. So we have mass 1 is equals to a cubed over p squared. Since a is equals to 1 and a is equals to 1, or a cubed is equals to 1, we have m1 is equals to 1 over p squared, which is equal to 0.71 squared. So we have 1 over 0.5 is equals to 2. So the mass of the star is twice the mass of our Sun. Remember that this way of expressing the law has units in terms of Earth and the Sun, so masses are expressed in units of the mass of our Sun. The orbits in the solar system. Recall that the path of an object under the influence of gravity through space is called its orbit, whether that object is a spacecraft, planet, star, or galaxy. An orbit, once determined, allows the future positions of the object to be calculated. 2 points in any orbit in our solar system have been given special names. The place where the planet is closest to the Sun and moves fastest is called the perihelion of its orbit, and the place where it is farthest away and moves the most slowly is the aphelion. For the Moon or a satellite orbiting Earth, the corresponding terms are perigee and apogee. Orbits of the planets. Today, Newton's work enables us to calculate and predict the orbits of the planets with marvelous precision. We know 8 planets beginning with Mercury closest to the Sun and extending outward to Neptune. The average orbital data for the planets are summarized in the table. In addition to the 8 planets, there are many smaller objects in the solar system. Some of these are moons that orbit all the planets except Mercury and Venus. In addition, there are 2 classes of smaller objects in heliocentric orbits, asteroids and comets. Both asteroids and comets are believed to be small chunks of material left over from the formation process of the solar system. In general, asteroids have orbits with smaller semi-major axes than do comets. The majority of them lie between 2.2 and 3.3 astronomical unit in the region known as the asteroid belt. As you can see, the asteroid belt is in the middle of a gap between the orbits of Mars and Jupiter. It is because these 2 planets are so far apart that stable orbits of small bodies can exist in the region between them. Alright, well that's the end of our session. I hope you learned something. Thank you and have a great day. Bye!